Hello and welcome to the 2022 Boulder workshop, where we're going to discuss hypothesis testing, effect sizes, and statistical power. My name is Brad Verhals from Texas A&M University, and I'm going to walk you through some of the important components of these concepts. So the first thing that we're going to start with is statistical power. And just to quickly define it, statistical power is the probability of correctly rejecting the null hypothesis. Importantly, statistical power depends on four components. The first thing is sample size. This is often what we're trying to calculate. The second is our alpha level. And typically we set alpha at 0.05, or the p-value of alpha equals 0.05 or less. The third thing is our beta level, our power level, the probability that we're going to reject the null hypothesis if the null hypothesis is actually false. And the final thing that we're going to do is we're going to look at effect sizes. And so in order to do this, we're going to start right at the beginning and think about how statistical power relates to the basic components of hypothesis testing. So when we're thinking about hypothesis testing, we really have three steps. The first step is to define what the null hypothesis is. Oftentimes, this is a hypothesis of no difference. So group A is equal to group B, or the parameter of interest that we're looking for, say our heritability coefficient, is equal to 0. Of course, at that point, we then define what would be considered sufficient evidence to reject the null hypothesis. Say p is less than 0.05, for example. In a genome-wide significance framework, we might want to say p is less than 5 times 10 to the negative 8, and that would be our threshold for rejecting the null hypothesis. And the final thing that we do is we go and collect data, and then we actually conduct our analysis and see where the parameters fall. So when we're thinking about hypothesis testing, then we can imagine a distribution of our test statistic under the null hypothesis. The next thing that we need to do is define this evidence that we're going to use to reject the null hypothesis. So in a standard situation where alpha is set to 0.05, anything that falls in this blue shaded region, we would claim is inconsistent with the null hypothesis, and therefore we will reject it. Now, even if it is part of the null hypothesis, we will observe that approximately 5% of the time, i.e. a p of 5%. The second thing that we really need to think about is the distribution of the test statistic under our alternative hypothesis. Now, most of the time, if we're going to conduct a study, we're not thinking, oh, nothing's going to happen. We're thinking, oh, something's going to happen. And what we believe is going to happen is that our test statistic is going to fall in this distribution, in the alternative hypothesis distribution. And so the probability that we're able to reject the null hypothesis, given that we're in the alternative hypothesis, drawing our statistic from the alternative hypothesis distribution, is going to be our power. And this red shaded area is the beta component here, 1 minus our power, which we can quite easily say is sometimes, even if our statistic is drawn from the alternative hypothesis, sometimes that statistic still won't reach our level of evidence that we require to reject that it's part of the null hypothesis distribution. The second component here that we really need to talk about is effect sizes. So effect size is a measure of the strength of a phenomenon in the population. And most of the time, when we're thinking about effect sizes, we're thinking about effect sizes independent of the sample size or other components of statistical power. In a lot of cases, this helps us communicate the result in everyday language, especially if the scale is meaningful on a practical level. For example, we might want to say that people who take Zyban or bupropion smoke 5 less cigarettes per day, or people who take Lipinox will lose 28.16 pounds in 8 weeks. That would be an effect size measure. Effect sizes are agnostic to whether the effect is real or not. So it could be a real effect, or it could be a false effect. And and the effect size doesn't really care whether it's one or the other, because they're not associated with p-values, as they don't incorporate any components of sample size into them. When we're thinking about effect sizes and we're thinking about the distribution of the null and the alternative hypothesis, the difference between the mean of the null and the mean of the alternative hypothesis distribution is what we're really thinking about when we're thinking about the effect sizes. So if we've got a regression coefficient of 0.2, this difference between these of 0 and 0.2 under null and alternative hypotheses respectively would be our effect sizes. So what are the conventional sizes of that we think of when we're talking about effect sizes? Well, most of this stuff comes from Cohen's classic 1988 book, where he provides some standards for interpreting effect sizes. And it's really important to be cautious when we're interpreting effect sizes, because in a rather counterintuitive way, large effect sizes are not necessarily more theoretically interesting and instead tend to be rather obvious. So when Cohen wrote his book, he noted that, well, a small effect, something with an R-squared around 1%, is likely to be something that we need to do some sort of statistical analysis to detect. We really do need to do some sort of modeling of our data in order to extract the association. It's not going to be observable just from walking around. A medium effect size, or an R-squared of about 0.1, is going to be apparent upon careful inspection. It might not be completely obvious, but it's going to be apparent if you were to really look carefully at the world around you. And then we've got large effect sizes, or an R-squared of about 0.25. And this is really going to be obvious at a superficial glance. Things like men tend to be taller than women, or something completely obvious like that. On average, that doesn't mean that all men are taller than women, but that on average, we wouldn't really need to do a statistical test in order to get this. Okay, so now that we've defined several of the components of statistical power, let's talk about what that really means. So statistical power is typically used to do two types of power analyses. The first type of power analysis is called an a priori, or a prospective power analysis. We typically do an a priori power analysis in order to figure out how many responses are necessary to fairly test our null hypothesis. This is typically done for grant applications or things of that sort, where we have to justify a sample size that we're planning on collecting. A second type of power analysis is called a post hoc, or a retrospective power analysis. And in this type of power analysis, what we're going to do is we're going to explore whether the effects that we've observed can be reasonably expected to reject the null if it's actually false. If we were to say add more people, how much power did we have in our test? Is our test based on about 20% power, 50% power, et cetera, et cetera? And knowing how much power you had to test your null hypothesis is really an essential element in understanding the likelihood that you're going to replicate your results. So if we think about the likelihood that you observe you reject the null or you fail to reject the null, we can think of a situation where we know what the truth is. So we can say that the null hypothesis is true or the null hypothesis is false. Of course, in reality, we never know what the truth is, but we can set this up as kind of a straw man. And then if the null hypothesis is true, but we reject the null hypothesis, we're committing a type 1 error, or a false positive. If, by contrast, the null hypothesis is actually false, and we fail to reject the null hypothesis, then we're committing a type 2 error, or a beta error. In this case, it's a false negative. Of course, if the null hypothesis is false and we reject it, or if the null hypothesis is true and we fail to reject the null hypothesis, then we're in a good state of affairs. So what is a type 1 error. So a type 1 error is this false positive. The rejection region that we're focusing on here is this red shaded region in this figure. And if our test statistic falls in this region, we will reject it, even if there's the effect isn't true. Basically, in this case, we just sort of got lucky. So given that our alpha is fixed probably by our discipline or at least exogenously from the experiment, this is the basic significance level that we're trying to test. By contrast, a beta error is the probability of failing to reject the null hypothesis when it's actually false. In this case, our statistic is drawn from the distribution on the right-hand side here, but it just happened to be really far out in the lower tail of our effect size distribution. And what that means is that it doesn't exceed the necessary alpha threshold to reject the null hypothesis. In this case, this is a false negative. So when we think about the standard conceptualization of statistical power, we're really thinking about those four elements. We've got our effect sizes, our sample sizes, and the alpha and beta levels. So if we take this simple equation and we arrange it, we can show that we've got our alpha level, our beta level, and the difference between alpha and beta is equal to the square root of our sample size times our effect size. And this works pretty well for a lot of cases when we're looking at differences of means, or we're looking at sort of correlations or something like that. Once we get into things like twin models, where we're looking at differences between distributions of correlations, things get a little bit more complicated. So instead of thinking about the standard power calculations, twin modeling tends to use two possible methods for calculating statistical power. The first method is a simple Monte Carlo simulation method, where you simulate a model under the alternative hypothesis numerous times, say 1,000 times, and then you count how many times you observe a test statistic for your parameter of interest that exceeds the critical value that you're looking for, so 0.05, for example. And the proportion of times you get this significant result is your statistical power. It's pretty simple to do. The downside of it is it can be very time consuming. Also, with models that are complex, this can take a lot of time, and you can end up with a lot of model failures that may or may not affect your statistical power. An alternative method is to use what we'd call non-centrality parameters. Because we're working with parametric tests, we know, or we assume, that the distribution of the test statistic follows, say, a standard chi-squared or a standard normal distribution. And we can leverage this assumption to more directly calculate statistical power without doing just an absolute ton of replication. So we can do it once and then calculate power from there, rather than doing it 1,000 times and looking at the proportions. And because of this time difference, the number of times you have to do it, this can be done relatively quickly. So we're going to focus on non-centrality parameters. So the non-centrality parameter is the sum of the mean of the test statistic distribution under the alternative hypothesis with a given set of degrees of freedom. That's a little complicated, but basically what we're talking about is the difference between the distributions that we've been discussing already, that effect size distribution. So there's 2 points that are especially important for calculating statistical power using non-centrality parameters. The first is, as the effect size gets larger, the mean of the test statistic distribution gets larger, and therefore the NCP gets larger. And as the NCP gets larger, we have more statistical power. The second component is, as sample sizes increase, the standard deviation of the null and the alternative distributions gets tighter, and therefore the NCP, the non-centrality parameter, gets larger as well. In both cases, as effect sizes get larger or as sample sizes get larger, we are increasing our statistical power. Okay. So when we're calculating power with non-centrality parameters and twin models, we've got 4 basic steps that we're going to follow. The first thing that we're going to do is we're going to simulate twin data that corresponds with the alternative hypothesis. Say we want to tell whether the power to detect an additive genetic variance component of 0.4, how much power would we need to do that? And so that would be something that we'd want to test. Of course, the level of your effect sizes, for example, how big your additive genetic variance component is, should be based on the literature as far as possible. Of course, if you're doing something really novel, you might not know how heritable it is, and so you'll have to take a guess. The second step is to fit the full and the reduced models to the simulated data to obtain a chi-squared value from the likelihood ratio tests. So if we're going to test the heritability or the additive genetic component, what we'd want to do is we'd want to simulate the data in step 1, and in step 2, we'd run the ACE model, and in step 2, we'd also compare that against a reduced model, the CE model. And we would be able to tell based on that how significant that A parameter was. Once we've got this chi-squared test from the likelihood ratio, chi-squared value from the likelihood ratio test for the full and the reduced, we can calculate the average contribution of each observation to the chi-squared. So in order to do that, we take the difference that we have observed from the likelihood ratio test and simply divide it by the total number of observed observations. In this case, if we had MZ twins, we divide it by the total number of MZ plus the total number of DZ twins, twin pairs. And this will give us what I call the weighted non-centrality parameter. And then we can go ahead and in step 4, we can actually calculate that. We can use this weighted non-centrality parameter to calculate this non-centrality parameter for a range of statistical sample sizes. And then we can just basically multiply it by any given sample size to get what our chi-square value would be for that particular value of n. So if we had a chi-squared value, for example, of 10 with 1,000 observations, the weighted non-centrality parameter would be 10, or our chi-squared value, divided by 1,000, which is our number of observations, to give us 0.01. Therefore, on average, each observation contributes about 0.01 to the NCP. Because the NCP scales linear with sample size, if we had 2,000 observations, we would simply multiply this 0.01, this weighted non-centrality parameter, by 2,000, and we would get a chi-square value of 20. If we had 500 observations, we would multiply this weighted non-centrality parameter of 0.01 by 500, and we get a chi-square value of 5. And it's really that easy. So all of the stuff that I've told you today comes from this paper that I wrote in 2017 for the Boulder workshop. And I'm going to walk you through quickly a power analysis based on the script that we've put together. All of the functions can be found in this powerfun.r script. And as a quick note, you're going to need to have the powerfun.r script in your current working directory, or the powerscript.r will not be able to find the functions because all the functions are in here. Okay. What we can do then is we can just walk through a couple of examples to show how this script works and show how you can calculate power using the non-centrality parameter in twins. And everything's pretty well boxed up. But of course, the devil's in the details. So we'll go through some of those details now. So the first thing that we're going to want to do is we're going to want to require the necessary R packages. And there's two in particular that we're going to use, OpenMX and MASS. So OpenMX is going to help us to specify and fit our twin models. and mass is going to help us to simulate the data. Remember, that's the key step at the beginning. And then what we're going to do is we're just going to source all of these functions, and running these 3 lines of code will allow us to start playing with some of the possible power analyses that we're going to want to look at. So I've set out a series of power analyses that we might find interesting as twin modelers. So the first question that we might want to know is, what is the power to detect A, or the additive genetic component, in the univariate model as C, the shared environmental component, increases? So what I've done here is I've specified 3 models. One where the additive genetic path coefficient is 0.6 for each of the models, and then the common environmental path coefficient goes from 0.3 to 0.7 to 0.5 to 0.7. And note here that we're assuming that the sample size for the MZ and DZ twins is equal. We've set it arbitrarily to 1,000, but this is actually something that it's much more important to get the proportion of twins right. So in this case, we're having equal proportions than to actually specify a specific number. Sometimes when you are fitting rather esoteric models, you might want to bump this up to, say, 10,000 or 100,000 twins in each group in order to get more precise estimates of the average non-centrality parameter, or the weighted non-centrality parameter. So if we run these 3 lines of code, we've basically set ourselves up to get all of the information that we're going to need. And we can look inside this object, say mod A1. And what we'll see here is 3 bits of information. First, we can see on the left-hand column of the top table the estimates that we specified. So we wanted a 0.6, a 0.3, and then R just computes what the rest of the path coefficients would be. So 0.6 and 0.3 would leave an E component of about 0.74. And you can see how closely these are being estimated to what we're asking for. And we can see what the standard errors are. And this kind of tells us what the results from our twin model would have been under this situation. We want to make sure that these estimates here match what we're seeing or what we're asking for in our function. If they deviate too far, then our simulation didn't work and we probably have to do it again, perhaps with a larger sample size. The 2 key pieces of information here that we want to know are going to relate to the A and the C parameters. So our weighted non-centrality parameter of A here is going to be this value here, 0.0121, et cetera. And the value of C is going to be 0.00105 or so. And we can see that this value here for A and this value here for C correspond, or at least proportional to the non-centrality parameters, giving us some suggestion that what we're seeing is going to be useful. So now that we've actually calculated the weighted non-centrality parameters for A, we can then just plot them. And so the power plot function that is cooked into this power fun functions will allow us to plot all of the various non-centrality parameter power analyses that we're interested in doing. And if we just run those 4 lines of code, it's going to give us a legend as well. And what we can see here is that on the x-axis, we've got the sample size that we're looking for. And on the y-axis, we've got the power to reject the null hypothesis, or the power to detect a significant parameter. Now, if we look at the black line here, that was our first situation where A was equal to 0.6 and C was equal to 0.3. So we can see here that as we increase the power, we finally get that magic value of power equals to 0.8 when we get about 625 individuals. By contrast, if we increase C from 0.3 to 0.5, which is this red line here, we can see that the power to detect the A component increases much faster. And if we increase it again to 0.7, it is increasing even faster. Basically, what we can see here is that the power to detect A depends on the assumptions that we have about the power to detect C, which is very interesting. And it has a big effect on this. If we look in our R console window, what we can see is our 80% power to detect an A of 0.6 when C is 0.3, we would need about 645 twin pairs, split evenly between MZs and DZs. If we had a C of 0.5 and an A of 0.6, what we'd have is about 400 twin pairs necessary, so 200 MZs, 200 DZs. Now, if we have a C of 0.7 and an A of 0.6, which is explaining pretty much all of the variation with either the additive or the common environment, additive genetic or common environment, what we'd see here is we only need about 51 MZs and 51 DZ twin pairs, which is an astronomically low number of twin pairs. Okay, so the next question is, what's the reverse? How does the power to detect C vary as we increase A? So instead of increasing C from 0.3 to 0.5 to 0.7, we increased A, and we kept pretty much all of the other parameters the same. And so all we need to do here is run this. And if you wanted to test different values here, you could just replace any of these values, and we can run that. And then we can similarly plot this using the same functions, basically. And what we can see here is that the power to detect C depends much less on our value of A than the power to detect A depended on our value of C. So what we can say here is we really have to have some expectation of both A and C included in our power analyses. Okay. So up to this point, we've looked at the power to detect A and C when the sample sizes were equal. In this next section, what we're going to do is we're going to look at two very different two different sample sizes and how they affect power. So we're going to say we've got a 5-to-1 ratio, so 5,000 to 1,000 ratio of MZ to DZ twins, and then we've got an equal ratio, and then we've got a 1-to-5 ratio of MZ to DZ twins. And just for simplicity, we'll keep it at 0.6 for the A and the C component, but this demonstration doesn't really depend upon the values of A and C. What we're looking for is the proportions that of the various twin types that we have. And so again, all we need to do is quickly run this, these 3 lines of code, and then we can plot the power. And if we were to quickly plot that again, what we would see is the plot would shape up much nicer. Okay, so what we can see in the power analysis where we vary the proportion of MZ to DZ twins from 5-to-1 to equal to 1-to-5 is that the best power comes, or the smallest sample sizes come, when we have about equal numbers of MZ and DZ twins. A lot of times people think, hey, you know, in order to get more power, I should have more MZ twins, but that's actually not the way that we would see this shaking out to detect additive genetic variants. Of course, to detect common environment variants, it's actually much more beneficial to have more DZ twins than MZ twins. And if we have MZ twins, we're dramatically underpowered to detect the common environmental components of variants, which is an interesting and important finding that we need to keep in mind when we're doing our twin analyses. Okay. The next thing that we have to keep in mind is whether we're using continuous or categorical, and let's, for the current analysis, look at binary data, so case control data. And what we can do here is we can think of how the prevalence of our case control trait affects the power to detect a significant genetic component. Now, let's say that the genetic component is, again, a path coefficient of 0.6, and the common environment is a path coefficient of 0.6. So we've got equal A and C here, and we've got equal proportions of MZ and DZ twins. So all we need to do to start out with is specify all of the various different coefficients that we might be interested in running, and then we can plot it again. And as we can see here, as the prevalence goes from about 0.5 down to 0.05, the power drops dramatically. So for our common traits, we can get away with many fewer twin pairs, say about 1,100 for a prevalence of 0.5, whereas for a prevalence of 0.05, we're looking at over 4,000. And we need to keep this in mind when we're doing any types of twin models. Okay. The final set of power analyses that I want to talk about is the power to detect genetic correlations between our variables. So what we've done here is we've specified an increasing set of A and C, or of A for the first trait and A for the second trait. And what we're looking at here is increasing the genetic correlation between these two traits from 0.1 to 0.3 to 0.5. So very small, moderate, and actually quite large genetic correlations. And we're keeping the C correlations proportional to the A correlations. And then we're going to keep the sample sizes approximately equal again. All right. So if we run these 9 different scenarios, what we've got here is all of the results that we need. And now we can easily plot those. And we can take a look at what comes out. So for both, because both the variable 1 and variable 2 were simulated to have the same A, C, and E components, we can see here that the power to detect those variance components is equal for both traits. What we can see is that we need about just less than 600 twin pairs to detect an A of 0.3, about 200, just over 200 to detect an A of 0.4, and just about 100 to detect an A of 0.5. Importantly here, the power to detect our genetic correlations varies pretty dramatically with the amount of heritability that we have in our traits. So for modestly heritable traits, we can only really reliably detect a genetic correlation of about 0.5. So with an A of 0.3, we're looking at about 1,200 people, 1,200 twin pairs in order to get our correlation power up to the 0.8 level. By contrast, if our A is about 0.4, we need about 500 people to get that the significant genetic correlation power to 80%, whereas we need about 1,400 to get it for the modest genetic correlation of about 0.3. And then by the time that our A parameter gets to about 0.5, we have even more power. And of course, when we have a very small genetic correlation, we never really achieve sufficient power with reasonable sample sizes. Okay, so just to recap, we've gone over the elements of statistical power, hypothesis testing, and effect sizes. And we've gone over a variety of different methods of calculating them. And I've shown you a demonstration of how you can use some of the functions that we've put together over the years to calculate power for a classical twin design. Thank you very much. My name is Brad Verhulst, and you can ask me all of the questions that you need in the workshop practicals, where we'll go through a little bit of this information as it relates to estimating twin models. Thank you very much.